If you look at this image on the left here, we have a complex ion. There is a transition metal in the middle, and then there's ligands around it. And this whole entire thing, because it has a charge of -2, it's called the complex ion. The complex ion has, again, this ligand, and I'd like to discuss the different types of ligands the complex ion or even coordination compound would have. It's complex. This particular ligand is considered to be a monodentate. Monodentates they just have one lone pair that is donated and is going to connect with the transition metal as a ligand, just only one. So if you look at water, it could donate one pair here. Now you might wonder, well, what's the other one? You can donate that too. Yes, that is true, but it's only from that particular oxygen. And what about for fluorine? No matter which lone pair it attaches to, it's just fluorine. What about cyanide ion? You might wonder, well, it could donate to from here and here, so from the carbon and the nitrogen, since they both have a lone pair. That is true. But once it is connected to, say, on the carbon side to the transition metal, that's it. You can't connect the nitrogen side both at the same time. So I should sort of clarify the definition of monodentate is that only one pair is connected to the transition metal as a ligand, and if there are more, there isn't going to be additional connection afterwards. Let's look at thiocyanide ion. You see S, C, and N, and the sulfur and the nitrogen are the only ones that with the lone pair. So it's either going to be attached to the sulfur or it's going to be attached to the nitrogen and not both. So these three on the complex ions are examples of monodentate that is connected to a transition metal. Let's look at the cyanide ion. It's connected from the carbon, whereas silver here, it's connected from the nitrogen, from ammonia, and you have a copper that is attached to the chloride ion. Now, these are, again, all example of monodentate. These are ligands that have the ability to attach to the transition metal by donating a pair of electron. This list of a monodentate is in your reference sheet. Now, before I go into the next type of ligand, I'd like to sort of do a little review, and that's right at the chemical formula based on the structure above. So here are some structure, and let's go ahead and write out the chemical formula. So we have our bracket here, so I'm going to put my bracket. And first we write the transition metal, which is our zinc. Then we are going to write the ligand. This one has it's cyanide, so it's Cn. And there are 4 of them, so hence 4. Close the bracket to let the reader know that the cyanide is all attached to that zinc. And then it's got a charge of -2. It doesn't have any counter ions, so it has a charge of -2, so we write that. Let's try for the next one. Here's silver, and then I have ammonia, and that's in parentheses. There's 2 of them, and then a bracket plus. Next one, here's another bracket, copper, and then we have 4 chlorines, and then we have 2 minus. Next, we have bidentate. So this is another type of a ligand. This type of ligand has 2 lone pairs that are connected to the transition metal as a ligand. So the 2 lone pair has to be far away from each other so that the molecules can bend and connect to the transition metal. Here's what I mean. So here's an example of bidentate, the ethylene diamine and the oxalate ion. Ethylene diamine is also known as En when we're writing the chemical formula. So comparing this bidentate versus monodentate, for example, cyanide. Well, what's the difference? The difference is that the ethylene diamine, it's very long and has the ability to bend. Even oxalate ion, it has the ability to bend as it's donating 2 pair of electron. Cyanide is not very bendable. It's just really constricted by that triple bond, and there's only 2 right next to each other, so it's hard for them to bend. So therefore, they cannot connect 2 lone pairs, one from a carbon and one from nitrogen, to form a ligand with the transition metal. But something like ethylene diamine and oxalate ion, because they have the ability to bend and the lone pairs are far away from each other, both of these guys can bend to the transition metal. So you see cobalt here, and this is one ethylene diamine. Here's another one, and here's another one. Okay, so all of those are sort of bent in structure in order to bond to the cobalt ion transition metal. And then here's iron with the oxalate ion. You see the bending that is occurring. Okay, so let's do some problem here. Write out the chemical formula based on the structure above. So something like this. Again, it will have a bracket with cobalt transition metal in the middle. Written first, and then you have ethylene diamine. So ethylene diamine, since it's abbreviated EN, it's rather easy. So you're going to put parentheses EN, and how many ethylene diamines are there? There are 1, 2, 3. So you're going to put subscript 3 and has charge of +3 right here. What about for this guy? This one has iron, so you're going to write the iron first. Then the oxalate ion, well, that's you're going to count how many carbons there are. So there's 2 carbons, and there are 4 oxygens for every 1 oxalate ion. I'm going to parenthesize this, and you'll notice that there are 3, right? 1, 2, 3, and then I'm going to go ahead and put the bracket in there. Now, what's its charge, okay, or it doesn't even have a charge? Iron is known to be +3. All of these oxygen molecules have negatives, so 3, and then there are -6s. So -6 and a +3 balances out to be -3. So therefore, charge will be -3. All right, let's do a learning check based on what we have learned so far. Draw out. Now, you're going to draw out the complex ion with ethylene diamine and determine the coordination number. Let's do first one with me together, and then you'll try the next 2. So here's my nickel, which is my transition metal, and it's got water. Water, if you look in your reference sheet, is known as a monodentate. And then I have my EN, which is the ethylene diamine, and that's my bidentate, since it's pairing 2 are being donated. All right. And that's got a charge of +2. So very easy. We're going to go ahead and put a bracket like this and give plenty of space. And then we're going to put +2 because I keep forgetting putting the charges in the end. So I'm going to put it now. We put the nickel in the middle, and notice how many is attached to, how many numbers of molecules are attached to the nickel. So you'll notice there's 4 waters being attached and 1 ethylene diamine. And this is a monodentate, right? Monodentate, where EN is a bidentate. There's going to be a total of 6 coordination in order for it to bond to nickel. Here's water. So say we are attaching to water. So I'm going to draw one going up and down, one that's going back, and a wedge that's coming out. So this is giving me an geometry that's showing that it's coming out of the page, and the squiggly line or the dashed line is going back, while the ethylene bidentate, ethylene diamine will have the nitrogen that is attached to the nickel, and then it's got the CH2 and a CH2, and then it has NH2 again that is going to attach to the nickel. Then we have our water. Water is the oxygen is going to be the one that has the lone pair, so oxygen will be here, and I'm going to write the rest of the hydrogen. Same thing. There's 4 oxygen. Okay. All right, so this would show what the complex ion would look like. Now, you might be wondering, why didn't you connect this to maybe say here with the bottom one? That's because the ethylene diamond isn't long enough. They have to be the one that's next to each other. So we're going to try the next one and come back. And here is the key.